Okay, I want to teach you about another application of propositional logic. For anybody who's done some programming, you may be familiar with the idea of a logic error in your code. There are a lot of different types of logic errors, but one of them is the possibility that you may have an inherent contradiction between logical statements. This is called inconsistency. So the idea of consistency of logical statements is that statements are consistent with one another if it's possible for them all to be true at the same time. If it's impossible for all of them to be true, then they're called inconsistent, and the reason is that there will be some inherent contradiction between them. So this idea is related to another idea called propositional satisfiability. So an overall compound proposition is called satisfiable if there exists some truth values for its variables that will make it true overall. Otherwise, if it's not satisfiable, then that would mean that no matter what values you give the variables, it's going to be false, which means that it's a contradiction. So when you ask a question about consistency of logical statements, this can be rephrased as the question, is the conjunction of these statements, which I could write as P implies Q and P implies not Q in this example, is the conjunction of these statements satisfiable? If it is, then they are consistent. If it's not satisfiable, then they're inconsistent. So we could just check by sort of assigning values to things, and we could search maybe by trial and error for some kind of an assignment of truth values that's going to make this work. In this case, they are satisfiable. In this case, the answer is yes, since both implications will be true vacuously when P is false. So if P is false, P implies Q will be vacuously true, and P implies not Q will be vacuously true, regardless of the value of Q, so it doesn't matter. So Q can be whatever you want. As long as P is false, this will be satisfied, which means that these statements are consistent with one another. Perhaps not in a very satisfying way, like they're not particularly, maybe it's not very useful for them to be consistent with one another if the only way that's ever possible is when you have vacuous truth, but at least they are consistent. So let's do a second example. Let's say that I'm going to take the same statements. One is P implies Q, and two is P implies not Q, but let's say that we want P to be true. So the third statement will be just P by itself. So now with these three statements, are these consistent? Well, you might think maybe they're not, because if P is required to be true in order for statement 3 to be true, then if P is true, P implies Q would mean Q has to be true. But P implies not Q would mean that not Q has to be true, which means Q is false. So there's going to be a problem. There's going to be an inherent contradiction. I'm going to show you how we can write up a proof that this is not consistent. So the proof that these are not consistent. We're going to use a strategy called proof by contradiction. Now, this strategy, we're going to go into much more detail on this later in the chapter, and we're going to practice using it. And I'll get into the gist of it. But in this case, we're going to start by assume that the statements are consistent. What we want to do is prove that they're not consistent. We're assuming that they are consistent, and then we're going to discover by that assumption, we're going to discover a contradiction. And that will show that that assumption we made must have been false, and therefore they're not consistent. So if we assume these statements are consistent, then that means we're going to be assuming that this conjunction, P implies Q, and P implies not Q, and P must be true. So in order for a conjunction to be true, all of its parts have to be true. That means P implies Q is true, P implies not Q is going to be true, and then P is going to be true. Now, since P is true and P implies Q is true, The only way that's possible is if Q is also true, right? Because if your hypothesis is true and your implication is true, the conclusion has to be true. So then we can conclude that Q is true. I'm going to put a box around that, okay? And also, if P is true and this implication, P implies not Q, is true, well then not Q must be true by the same reasoning. Not Q is true. So if not Q is true, Q is false, right? Because the negation of Q has the opposite truth value to Q itself. So if not Q is true, Q is false. So we've just concluded, by the assumption that these are consistent with one another, we've concluded that Q is true and also that Q is false. These can't both happen at the same time. Law of the excluded middle says that a proposition has to be either true or false, not both and not neither. So there's no possibility that that we can have these. This is a contradiction. And we can say, therefore, the statements are not consistent. And end with a QED. I ran out of space at the bottom, but that's okay. So that's an example of how to prove that something is satisfiable. All you need to do is demonstrate that it's possible to make it true. In this case, all we needed to say was, yes, both of these can be true if P is false. But then when we looked at the second example, with a third statement, we were able to prove that it was not consistent by this method called proof by contradiction, where we assume it is, and then by assuming that all the parts are true at the same time, we actually discover an inherent contradiction, which shows that that assumption must have been false. So there we go. That's the last application we're going to look at today. There's tons of applications of propositional logic, and we're going to continue working with it as we go throughout pretty much the whole semester.